Okay, you know, before I go into the slide, uh, this lecture, I think I should. But before that, I want to make sure that, we are clear on some of the definitions of probability. So, yeah. So, we'll start with the very basics and then we'll do the ML part. So, okay. Let's see. Okay. So, so I guess all of you are familiar with, you know, uh, probability at high school level or something like that. Basic, you know, what is the basic definitions of probability and all. Like, if not, then like we'll do it again. But uh, yeah, if you are, then it might help you. So, okay, with that, let's start. So there are like a few definitions that I want to make it clear before we go into numericals. So first is experiment. So what is an experiment? So experiment is something when you uh, perform a task which has some outcome. Uh, I mean, it's very hard to objectively define an experiment, but with I can give you some examples which will help you understand better. For example, you're tossing a coin. You're doing some task, tossing a coin. The coin lands on heads or tails. So that is the outcome of your experiment, and the task is you're tossing the coin. So that is basically an experiment. The whole process, right? Next term that we will see is sample, right? So experiment, as I said, is tossing a coin, or rolling a dice, for example. That is a good experiment as well, right? Now, sample. What is the sample for the first experiment? Let's consider the first experiment. What is the sample for tossing a coin? Like you can get either heads or you can get tails. So that is your total sample space, right? You cannot get anything other than that. Right? What is the sample for rolling a dice? You can get a value of 1, 2, 3, 4, 5, or 6. A six-sided dice, right? This is your whole sample space. Okay. Now, event. Okay. So event is, you know, you are, selecting a particular value from your sample space. So let's say, your x is some variable which can take either heads or tails. So x is the outcome of your experiment, which is tossing a coin, right? And that variable can take either heads or tails. And the event is when x takes a value h. That is one event. Or another event could be x takes a value tails. Okay, right? So that is another event. So these are events, right? So from the very basics, as I said, I will explain everything from the very basics, from the definition and all. Like, so is it clear till now, or you need any clarifications? We're just getting started. Okay. Okay. Right. So, okay. Now, before going into the definitions of probability, let's look at one rule called multiplication rule. Okay. So, I'll explain it with an example first, and then I will describe the rule. So let's say you go to a shop, you know. So you can either buy ice cream or you want to, drink, some soft drinks. Okay. So you have two choices, right? Now, if you decide on choice ice cream, you can choose whether you want vanilla flavor, whether you want, butterscotch, or maybe you want, let's say, chocolate. Right? On Coca-Cola, Pepsi, or let's say thumbs up, right? So yeah, now so this is more like a diagram, right? So what it says that you go to a shop, you have initially you have two choices. Okay, so this is the result of your first experiment. Okay, let's consider this to be a first experiment. So what is this experiment? This experiment is basically uh, you want to choose between ice cream and soft drink. This is your first experiment. Second experiment is that if you, let's say, choose between ice cream, choose ice cream, then you get to choose you know three more flavors of ice cream, and if you choose soft drink, you get to choose between three more flavors of soft drinks. Okay, so this is your second experiment. So you're doing two experiments, right, simultaneously. And the outcome of the first experiment is either ice cream or soft drink. Outcome of the second experiment could be, these things for ice cream, these things for, soft drinks, and so on, right? So the multiplication rule says that if you have, you know, n1 outcome for n1 outcomes for first experiment, and corresponding to each of those n1 outcomes, you have n2 outcomes for so on. You will end up with total n1 times n2 times dot 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 times of outcomes, total outcomes, right? So that is basically okay. Let me see. It's getting out of the screen. Okay. 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 So basically, yeah, this is the multiplication rule for n1 outcomes. For each of those n1 outcomes, if you have n2 outcomes for the second experiment, your total outcomes will be n1 times n2 times dot dot dot. So basically, for the first experiment, you have two outcomes here. For the second experiment, for each of those two, you have three more outcomes. So total number of outcomes will be six. These are the six outcomes. So it seems very simple and trivial, but how these simple things will lead to very will be very important while calculating probabilities and so on, right? Okay. Another thing I want to highlight before we go on to describe probability. So let's see. Okay, I'll write it here. Okay, so this is basically part of something called combinatorics. Okay, uh, you might have heard it in high school or so on, but we'll need only one result from this. So let's say you have n items, could be anything, n balls, let's say, or n boxes or whatever, n identical items, and you want to choose k items from there, you know, without replacement. Okay. Okay. So you want to choose k items from the n items without replacement, right? So first part is order uh, matters. Okay, let's consider this first. So by order matters, I mean like if you choose the okay. So I think I misspoke earlier when I said identical items. Let's consider distinct items for now. Okay, these are not identical items. These are distinct items. Let's say if you have like 10 balls, they will be numbered like 1, 2, 3, 4, 5, 6, 7, 8, and so on. So okay, so you want to choose uh, k balls out of n balls, and the order in which you choose the balls, that matters. So if you, let's say, picked up the uh, number 5 ball first and number 2 ball second, and the other way around, if you picked up the number 2 ball first and number 5 ball second, those two are distinct ways, right? Different ways. So basically we have to calculate in how many ways can we like do this. Can we pick k items from n items um, without replacing them, and the order will matter. So there is like, for the first item, you have like n number of choices. You can pick any one of the n items, right? You have n choices. For the second item, you have n minus 1 choices. So this is again like coming from the multiplication rule, right? For each of the n balls you have picked, for picking the second ball, that is performing the second experiment, you have n minus 1 choices. So we'll multiply this, right? N minus 1. And then again for picking the third ball, you have n minus 2 choices, right? And so on, right? Till n minus k plus 1. Okay, right? Is that fine? We're just using the multiplication rule that we just used earlier. Is it fine? Uh, okay, okay. Let me. Is it fine now? Okay, now it's better. Okay, okay. Now the second part is where order doesn't matter. So again, like you just need to find a group. So for example, this will be helpful when like you are, let's say, you are forming a team. You want a team of uh, let's say 3 people, and you have 10 persons in choice, right? So let's say the uh, let's say BCCI is forming the cricket team. They want like 15 players from a pool of, let's say, 100 players, right? So your n is 100 and you want 15 players. Your k is 15, right? So you just want to, I mean, order doesn't matter, right? You pick Virat Kohli first and Rohit Sharma second, or Rohit Sharma first, Virat Kohli second, doesn't matter. They will be in the team together, right? So this is the place where this order doesn't matter part comes in handy. And so the question is like, in how many ways can you uh, can anybody tell me the answer? Yeah, cricket team or football team or so. What is the answer? Can anybody tell me? Or like you don't know? Should I go into details? Yeah, Pritham is saying NCK. Everybody understands like what is uh, NCK, right? Or N choose K and so on. Okay, right? Okay. So the answer is like, yeah, 100 choose 15. or 100 ck, whichever way, like 100 factorial divided by, you know, 15 factorial divided by 100 minus 15 factorial. Okay. In general, n choose k is equals to n factorial divided by k factorial times n minus k factorial, right? So this will give you the value of number of ways you can choose uh, 15 people out of 100 people, right? Okay, so uh, okay, so in the first part, right? Okay, that's actually a very good question. You know, why it is n minus and why not n minus k? Uh, n minus k, yeah. So basically, if you see, you want to pick k items, right? So let me explain it this way. Like, if you had to pick, two items, let's say k is two. Okay. So what will happen is, what will you do? You will choose n for the first item, and you have n minus one uh, possibilities for the second item, right? Plus one. If k is 2, this will give you n minus 1, right? So if you go till n minus k, then you will, have an 2. So we'll have three terms, right? Is that clear? Okay. Yeah, but that's a very important question uh, because that is pretty confusing sometimes, right? So you have to keep in mind that, so basically in this series, this is actually the kth term, not the k plus 1 term. This is the k minus 1 term, not the k minus 1 term. This is basically the kth term. So you are choosing, if you count, 1, 2, 3, 4, so on, this will come out to be the kth term. So you need to choose k items and you need to stop at the kth, right? So I think that is clear. Okay. Uh, okay. Uh, which is not clear, and you don't understand NCK or. Okay, okay, okay. So the concept is, again, as I was saying, with the example that you need to pick a team of 15 out of a pool of 100 uh, people. So it doesn't matter if you pick let's say Virat Kohli first, or you pick Rohit Sharma first. It doesn't matter. They will be in the same team, playing in the same team. So in the first part, you are like ordering the people. So if you're picking a team and you are ordering them in terms of their playing position, then this is the number of ways. The first part is the number of ways. If you want to pick a team and arrange them in the playing order. Whereas in the second, what is asked is you don't need to arrange them in the position play, but you just need to select the group which will be playing. Clear now? Okay, Mr. Mova has raised a hand. Yeah, Mr. Mova. Okay. If not, let's move on to the next topic. Okay. Okay, let me open a new uh, tab. Okay. Let's see. All right. Now let's let's go into the definition of probability. Okay. So I will define probability in two ways. Okay. One would be the very naive definition. Another would be a more, formal definition. So naive definition is, so you have, let's say, again, let's go back to our favorite example, like tossing a coin. But this time, instead of tossing one coin, let's make it a little challenging. Let's toss the same coin, but twice. Okay. Or, you can see it as tossing 2 coins. Yeah, similar. So what will be your sample space in this case? So your sample space could be, you get head in both the coins, or head in the first coin, tail in the second coin, and the reverse thing, tail in the first, head in the second, or tail in both the coins. Okay. Now someone asks you that what is the probability that you get head in both the coins, right? So the naive definition is actually number of favorable outcomes divided by total number of outcomes. Okay. So in this case, what is your favorable outcome? Your favorable outcome is only, heads, this thing, both heads. So that is one. Divided by total number of outcomes is basically four. These are all the four outcomes that you have, right? So that is the, very naive definition of probability, right? Is that fine? I think this should be okay. You can come up with other examples of your own. Okay. Now, going into the more formal definition of probability, which is a more like an axiomatic definition of probability. So here, let me first draw a picture. So let's say this is your sample space, okay, and you have various points in your sample space. Each of the points represent each of the outcomes. So let's say this represents, HH, this represents another point represents HT, another point represents TT, and so on. Like you could, you know, toss 1,000 coins and your sample space will be filled with, many more outcomes and, you know, and this is basically your sample space. This is basically all the points in your all the outcomes basically, right? Now think of probability as a function that maps all the, subsets of all the possible subsets in your sample space to a number between 0 and 1, both inclusive, right? uh, is that making sense? Am I being too abstract? Sorry, which is not okay. So you know what a function is, right? A function is something which maps anything from domain to a range. So function. So let's say this is HH. This point in the sample space represents HH, as we are seeing in the previous example, right? And probability is basically a function or a mapping which takes HH to the value 1 by 4, right? So as we saw in our earlier example. So therefore, if you put machine, you give it some input, it gives you an output, right? That's the simplest way to look at it. You give an input HH to it, it gives you an output 1 by 4. If you give it an input, let's say HT, it gives you an output, again 1 by 4, right? Or, in this case, 1 by 4 could be any other number in general. Okay. It's just a machine which takes an input from your sample space and provides you an output of number between 0 and 1. Is that clear now? Okay. Okay. Uh, but I think if there is some particular question, we might answer that, but the Bayes theorem and all those things. But yeah, if so we'll cover a little bit about distributions, little bit, but yeah, we'll not go into much detail. First rule is that the probability of an empty set is equals to 0. Probability of the total sample space is equals to 1. That is the first rule, right? Now, so again, what is empty set? So this is your sample space. So what is that, this whole sample space occurs? It is 1, right? Even if like, any particular event from the sample space occurs, uh, that is included within the sample space. The sample space is represented by S. So probability of S is 1. So all all the outcomes are within the sample space. So the probability that an event occurs within the sample space is obviously, 1, right? It has to occur. Whereas null set is, the outside of the sample space, whichever is not contained in the sample space. So that probability is 0 because all your outcomes are contained in the sample space. So what is the probability that, some outcome outside the sample space occurs? It's 0, right? It seems pretty trivial, right? But this will have, very big implications when we derive some of the rules. Okay, second axiom is, if you have, uh, let's say a1, a2, an, these are n disjoint uh, samples, or n disjoint events, or sub. Yeah, I will write events. Let's say. Okay. Yeah, I'll write events. So if you have n disjoint events, probability of the summation of union of all the events. Two occurs, probability of the individual events, right? AI. So 1 plus P of A2 plus till P of AN. Right? I'll explain this axiom one with the help of something called Venn diagram. Right? Let me just explain it first. Okay. So let's say, this is your sample space, right? And this is, instead of considering n events, let's consider two events. So this is one event A, this is another event, let's say B. And this part is basically where both A and B occurs. A intersection B, right? So, okay, first, let me, do one thing. Instead of considering, because in the definition, as I mentioned, you have two disjoint events, right? A and B, right? So this is the meaning of disjoint. So disjoint basically means, if A occurs, B cannot occur. In other words, they are like mutually exclusive, right? So if you see, this is the event A and this is the representation of event B. And if A occurs, B basically cannot occur because they are separated, they are mutually exclusive, right? So what the axiom tells is that, P of A union B is basically plus P of P. So if you want to see, uh, so let me think of an example, right? So previous example, like tossing 2 coins, right? So tossing a one coin and you are getting head. So probability of getting head from the first coin is half, right? Each one. So, you know, so in the earlier case, while we are looking at this example, these two, when you are looking at the sample space, these two are not disjoint events, right? So one event are not mutually exclusive. So we'll have some intersection, right? But imagine, if you have events which are, mutually exclusive. So in that case, the probability will basically add up. So let's say if you have like probability of event A and probability of event B is this thing. Basically, what will happen is P of A union B is basically 1 by 4 plus 1 half. That will basically be, 3 by 4. That's it. Right? So is this clear? The only condition is that you can sum up probabilities when the two events are disjoint or mutually exclusive. Right? Okay. If the two events are not mutually exclusive, let's consider this diagram. Okay. This left side. So you have two events which has some, intersection, some P of A intersection B, right? Uh, Let me give one example. Let me think of some example. I think that will make it more clear. So let's say, you have, so in a class, you have number of students is 100. Out of that, number of males 60, number of female, let's say 40. Okay. And number of uh, students uh, who has let's say who has passed the exam is 70. Number of male students passed is, let's say 30. Number of female students passed is 40. Right, this is just a random example. So okay, so A represents the number of students who has passed. uh, Wait a minute. Okay, so let's consider, uh, let me think of another. Let's forget this. Let me think of something which makes sense. Okay. Okay. Forget about it. So let's say A represents the number of students who has passed in maths. Okay. Let's forget the male-female comparison, male-female example. So number of students who has passed in maths. Okay. So that is, let's say 70. Number of students who has passed in science. A represents the probability that uh, a student has passed in maths, probability that, and B represents the probability that a student has passed. So P of A intersection B represents the probability that the students has passed in both the subjects, science and maths. Example. Okay. Is that clear? Okay. So Kavita is asking when said multiplication rule is uh, so do you mean multiplication addition in case of probabilities like P of A union B and those things? So if you are talking about that, then I will explain in a minute when to use multiplication. So right now we are just adding up. We are just using addition because come to the multiplication part. So right now we are just adding up PA plus PB and calculating the total probability, considering that A and B are disjoint. But here, as I said, the events are not disjoint. So how will you calculate P of A union B, right? So that is the question. So if you see my screen, okay. So how will you calculate P of A union B? So you can break this. So this is the shaded region is A intersection B. To calculate what is the probability of P of A union B, this whole red shaded region. So the black shaded region is basically P of A intersection B, and the red shaded region is P of A union B. Okay, that I want to calculate. Yeah, that includes like you can basically that means in the previous example that I was giving, that means you have passed in either maths or physics, like not either, like if any one of maths or physics or science, whatever. So if you have passed in maths or if you have passed in both or any one of them, at least one of them. If you have passed in at least one of them, what is the probability? That is basically the example. Is that clear now? Whereas pay intersection B, that means you have to pass both P in both math and science. You understand the difference, right? P of A intersection B and union B. The probability, as I said. So considering, the second axiom, we will consider the second axiom. So as I said, A and B are not disjoint here. So what we will do is we'll break this whole set into two disjoint. So complement represents whichever is not in the set A. So if you see, P of A is this thing, this yellow shaded region, this is the whole P of A. Whereas if you see, P of uh, let's say P of B intersection A complement. So B intersection A complement is which is common between B as well as A complement. This is the green shaded region, which I am showing here, right? This is the green shaded region. So this term basically means the second term basically means that it should also contain in B as well as A complement, right? Now what we will do is we will break the second term into uh, two other terms, which is P of A minus P of A intersection B. Sorry, P of B minus P of A intersection B. So you can write the green shaded region as P of B minus the P of A intersection B, right? So the green shaded region is P of B minus the black uh, black line shaded region, right? Is that clear? So that's why the formula comes out to be like this. Yeah, this is basically the formula, right? P of A union B is P of A plus P of B minus P of A intersection B. Is that right? Or do you have any question? Okay. So from the first line, I am just writing PA as PA. Now I am writing this term, the second term, as this thing. That's just it. The second term basically represents the green shaded region, right? And the green shaded region can also be written as P of B minus P of A intersection B. That is if you like, P of B is again this whole circle minus if you just subtract the P intersection B part from. No, green part. So the green shaded part is basically P of B and intersection A complement. Uh, P A intersection B is not the yellow part. That is the black part in between, which is common between both A and B. That is this part, black shaded part, right? Yeah, which is basically the green part, right? That comes, so, right? Okay. Okay. So I'll just go back to my slide once and just, basically the first thing that I was trying to say, the formula P of A union B is equal to that thing. Again, if you see, this is the part B, P of B intersection A complement, and then you get the addition rule, right? This is the addition rule. So the first one is for mutually exclusive events. The second one is for, you know, non-mutually exclusive events, right? And now here is another thing which is called the law of total probability. Again, this is a very, very useful thing, and it simplifies a lot of problems. And okay, so I haven't gone through, conditional probability. I will come back to this after I, talk about conditional probability. Okay? I will come back to this law of total probability. Okay. So what is conditional probability? So, so you have understood, P of A, P of P, P of A intersection B, and so on, right? Now, if you are given something and you want to calculate the probability, right? If you know some information prior, beforehand, and you want to calculate the probability of something by knowing that information. So basically, you're conditioning on, you have some condition, that, okay, I know this. And then what will be a probability of something, right? So, for example, if I, go back to my tossing of coin example, right? If I go back to the, yeah, tossing, right? So, if I know that uh, the first coin is basically giving me, if I know that out of the two coins, the first coin is heads for me, okay? Then what will be the probability that, the second to find? So in this example, let's consider, I want to calculate the probability that the second coin gives heads, given that my first coin is head, right? To calculate. So if you see from this sample space, which are the examples, which are the events that shows that, first coin is head. So this is the first coin is head, and again, this one. These two are the only uh, events uh, which shows that first coin is heads. Now we want to calculate what are the chances that my second coin will also show heads. So that will basically, so your sample space is now reduced to only these two values. Your sample space is now only, this is the sample space, right? Now between these two, you want to calculate what is the probability also shows heads. So that is basically only this is your favorable outcome. So 1 by 2. Out of 2, you have only one favorable outcome. So you see, your probability has now increased. Your probability has been refined. Your probability has changed because you are adding one condition to it, right? So previously, the probability of head was 1 by 4. Now, since you know that the first coin is head and you want to calculate what is the probability of the second coin, this probability has increased, right? So this is a very, very powerful tool. And yeah, so we'll see how it is used in future. Okay. So, okay. Yeah, for by P of P, right? So again, I will explain through this example again. So P of H2 given H1 is basically P of H1 intersection H2 divided by uh, H1, right? So you have to calculate what is the probability that both are heads. So H1 intersection H2 is head. What is the probability? That is 1 by 4. If you look at, the original sample space. So now we will go to the original sample space. Okay. So what is the original sample space? HH, HT, TH, TT. Okay. So now what is the probability that both are heads? That is 1 by 4. You know. So in these two are the favorable outcomes, right? 2 out of 2 by 4. So this will basically give you half. Again, you see that is the same thing that we are getting. So explain the intuition, like why the formula is this, and this part shows that the formula actually works. The second part shows that okay, the formula now works, right? So is there any question now on this conditional probability? All right. So yeah, one comment on this is that so if P of H2 given H1 is uh, basically H2 if H1 and H2 are independent. So this is the condition for independence, right? So what does it mean? That you're tossing two coins. So the result of one coin is not dependent on the result of the second coin, right? Because you're tossing different coins individually, considering that both coins are fair, and the tossing of one of the probability that you get heads on the second coin is simply P of H2. And what is the probability that you get head on the second coin? Yeah, ha, 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 right? So again, all these things, this example can, is explaining all the things that I have, like the example has explained what are, as well as, conditional probability and, uh, you know, of events and so on, right? So, yeah, any questions? And again, if two events are independent, then P of H1 intersection H2 should be equal to P of H1, right? So again, so someone was asking like where to use multiplication, Kavita. So the dependent events, if you want to calculate what is the probability that both the event occurs, then you have to say that okay, P of what is the probability that I get head on the first coin? That is half. What is the probability that I get head on the second coin? That is also half. You get 1 by 4, right? Somehow in the notepad. Mm, Okay.